Here we have an optimization problem. We have a profit function, and in part A we are being asked to establish whether this profit function has an unconstrained maximum. And first we need to find the stationarity point or points. We don't have any quadratic terms in here, so it's likely to be only one. And we find that by setting the first derivative of the profit function equal to 0. So let's find the first derivative. The first summoned, the derivative is just a factor, square root of 2. Then we have the exponential function, it's replicated, and then using the chain rule times the inner derivative, which is just square root of 2. We can just slightly simplify this. Simplified for the purpose that's coming up. We just factor out the square root of 2, and this we want to set to 0. So here we have a product. Now that first term, square root of 2, is of course just larger than 2. So to get a first derivative of 0, this term has to be 0. And this term is 0 if the exponential part is equal to 1, because it reads 1 minus that exponential function. So we want the exponential function to be equal to 1. So now to answer questions like this, you really need to understand your exponential function and understand how it looks like. So, and we know that at a value, at an input value of 0, the function becomes 1. So that inner part, the argument of the exponential function, has to be 0. And that is going to be 0 if x is equal to 3. There's no other way how this can become 0. So this is our stationary point. In order to confirm that this is a maximum, as required or asked in the question, we of course have to look at the second derivative. So we want to judge whether the second derivative at that stationarity point, so at x equals 3, whether that is smaller than 0, as this is required for a maximum. So let's find out what the second derivative is. Pi 2 prime of x will go up to our first derivative here. It's possibly this form, which is the easiest to find the derivative from. The first term is just a constant, square root 2, so that doesn't deliver anything. So we have negative times the exponential function, which is just replicated, times the factor square root 2 that already exists, and now times the inner derivative, another square root 2 coming from the argument of the exponential function. So let's just slightly simplify that. That will be negative 2 times the exponential function square root of 2x minus 3 times square root of 2. So negative 2, this of course is always 0. The exponential function, if you understand the exponential function, is always larger than 0. So altogether this will be smaller than 0 everywhere for all values of x, because the exponential function will always be positive, even if the input is negative. So the second derivative of the profit function is smaller than 0 in the entire domain. That means it's of course trivially also smaller than 0 at x equals to 3. That means by that token x equals to 3 is indeed a local maximum, and as the function is concave everywhere, it is also a global maximum. So just to elaborate slightly on that point, we figured out that the second derivative of the profit function is smaller than 0 in the entire domain. So that means that our function f of x, or we called it pi of x, is concave everywhere. Right? So on all possible values for x. We actually only looked at the domain was actually for positive values of x, because that only makes sense in terms of production. But everywhere the function is concave. So we had our maximum at 3, and the function will look something like this. So here's our maximum profit that we have identified at x equals to 3. So let's look at part B of the problem. Now there's a constraint that has been introduced. 2x minus 4 times x minus 5 should be smaller or equal to 0. Now we're asked to use the Lagrangian method. So the Lagrangian will be equal to the profit function plus lambda times a constraint function. But the constraint function always has to be set up that it is larger or equal to 0. Our constraint was given smaller or equal to 0. So let me replicate the given constraint. If we multiply both sides of that inequality by -1, then on the left-hand side we get -2x plus 4, or we turn it around, 4 minus 2x, x minus 5, and then the direction of the inequality changes around, and that term we can use as our constraint g of x. Now we can write down the Lagrangian function. For our particular case, we should really put a lambda in here. Lagrangian is a function of x and lambda. And it is our profit function replicated. And then plus lambda times the constraint which we have just derived, 4 minus 2x times x minus 5. So what we will need for sure is the first derivative of this Lagrangian function. First derivative with respect to x. So here we go. The first part should look familiar from part A, and then we get a part from the lambda times the constraint bit, and here we have a product of two functions with x. So we will have to apply the product rule. So lambda times, and now we apply the product rule, -2 times x minus 5 plus, and now the derivative of the second one, which is 1 times 4 minus 2x. So that's an application of the product rule, which I of course expect you to know at this stage. So that part can be simplified, and if you check exactly how many x's and how many constants you have, you will find out that that last part simplifies to lambda times 14 minus 4x. So the conditions, if we apply the Lagrangian techniques that need to be given for us to find the maximum, is that L prime x is equal to 0 and the lambda is larger or equal to 0. And we will basically check two possible solutions: that where lambda is equal to 0, which is the unconstrained solution, or where the constraint function is equal to 0, which is the constrained solution. Let us start, and that's quite good practice to start with that. Let us start with the unconstrained solution. In fact, we've solved that already in part A. We know that the unconstrained maximum is at x equal to 3. And in some sense, all we need to check now is whether that solution meets the constraint. Is that inside our possibilities restricted by the constraint? So we look at our constraint function over here, and we substitute in x equals 3. So we have 4 minus 6 times 3 minus 5, and that is -2 times -2, and that is 4, and that is, as required, larger than 0. So a check. We are not falling foul of our constraint. As we already know, that our profit function is concave everywhere. And we therefore figured out in part A that our optimum at x equals to 3 is a global maximum, we know that no other restricted maximum could possibly be better than x equals to 3. So if you make this argument, you can stop the solution here. You have a complete solution using the information you gathered in part A. But what would you do if you either could not say that, or if perhaps you didn't see that immediately? You would try the constraint solution, and we do that by setting the constraint to 0. And we can see from this form that we get two solutions at x equals 2 and at x equals 5. These are the two values for x where that constraint is equal to 0. Then we would plug these values, x equals 2 and x equals 5, into our first derivative of the Lagrangian, and that is, we saw that on the left hand side, and we would then solve for lambda. And then we would have to check whether lambda is larger or equal to 0 as required. In this case, if you do so, you will find that the lambdas for both these solutions will be negative, and therefore these solutions do not meet our conditions. The condition being that the lambda has to be larger or equal to 0.